Welcome everyone to this evening's Berlin Functional Programming Group online end times meetup. It is my pleasure to welcome you once again. Before we get to our celebrated speaker, just a few announcements because I'm actually getting slightly more professional at this as I go on. So now I have a list of things I want to say. As I always say, the Berlin Functional Programming Group is hiring. We offer nothing, no salary, no benefits, only the reward of a job well done. If you want to help me organize this thing, I want help. I want speakers. I want other people to arrange speakers. We actually have a very nice platform now of around 1,000 members. So it creates a nice opportunity for all kinds of FP related events. And they don't all have to be talks. They can be hangouts, workshops. Shorter talks would be great if I can put a bunch of shorter talks together. You can organize a study group, like we have a Haskell study group now running weekly on Thursdays. You can discuss a paper you love. I know that's popular. Whatever, I'm up for whatever. Please get in touch. If you have suggestions, let me know. If you want to help me pay for my Zoom bill, you can buy a t-shirt. I'll drop a link into the chat. And that's appreciated. I am definitely not going to get rich from this, but if you'd like a really awesome t-shirt that will make you look extremely sexy because everyone will know that you are a functional programmer, then that's another advantage to buying one. Follow us on Twitter, Berlin FP Group. Please remember that this meetup will be recorded and posted to YouTube later in case that is an issue for you. And if everybody wants to let us know where you're from, just post it into the chat. I'm in Berlin, and I'd like to know where all of you are from, so just go ahead and drop it in there. And then it is my pleasure to introduce my friend, the fabulous, wonderful, amazing Brooklyn Zelenka. In addition to having quite possibly the most awesome name that I have ever encountered in my life, Brooklyn is the co-founder and CTO of Fission, and she's going to be talking about some of the work that she is doing there tonight. She is as her bio says, working hard on leveling the playing field for web devs by using new technologies and standards to eliminate the need for a backend and DevOps. So what I got from that was eliminate the need for DevOps. This strikes at my soul. I would love to eliminate the need for DevOps. Tell me how it's done, Brooklyn. She's also the founder of the Vancouver Functional Programming Meetup and is well known. In fact, this is, I think, how I originally knew about her, for translating large chunks of the Haskell prelude into Elixir. In fact, I think when I met her, I said, "Aren't you the Elixir person?" And I don't know that Brooklyn appreciated that direct relationship because she does a lot more than just Elixir, but apparently you're still doing Elixir events, Brooklyn, so you're not totally out of that world yet. Oh, and you've also worked on Ethereum. I hope that you've, squirreled away some of that for the end times that we're in, when all other currencies will probably lose their value and we're going to be back to bartering. But maybe there's going to be a place for digital currencies as well. I am very excited to have Brooklyn with us because I think basically what she's working on is extremely awesome. And not only is it awesome, it is built in Haskell, or at least partly built in Haskell. We're going to find out. So functional programming principles are at work to make the programming world a better place. And if you are ever stuck in one of those annoying arguments with someone who doubts the merits of FP, now you're going to have another example of something amazing that has been built using FP. And I think that's going to silence all future arguments. So I hope I haven't built you up too much, Brooke, but I'm very pleased to hand over the meetup to you now, and I'm looking forward to seeing what you have to say. Thank you very much for joining us.
Great. Well, thank you so much for inviting me and for that really lovely introduction. I'm just going to share my screen here for the slides. And do you see full screen stuff?
Yep, I see it.
Excellent, great. So this is a modified version of a talk I gave in Sweden back in the fall, updated with the sort of the new things we've been working on, but also adapted for more of an FP audience as well. And it's really meant to do things in fairly broad strokes, I was saying before we got officially started that I could talk about this in technical depth for many hours, but there's a lot of concepts that people may not be familiar with. So I'm just trying to really kind of give these broad strokes, how this is even possible and the way that we're thinking about things. This is my fairly standard about me slide, which we've basically already gone through. The little bit of color I'll give extra is, so beyond just being built with FP Tech, and there's a slide about that shortly, we're also very much informed with a functional mindset in general at Fission. So the solutions that we're coming up with are very much this sort of stateless, data-first, data-oriented way of thinking that need to be reproducible and, basically, as much as possible, keep things pure, right? I have a background in programming language theory, virtual machines, and distributed systems. And yes, I previously participated as an Ethereum core developer. So Ethereum's the world's second largest blockchain, and its sort of claim to fame is it was the first Turing complete, fully programmable one. The virtual machine has some challenges in it. So most of my efforts, I kind of worked all through the stack there, but most of my effort was aimed at improving the VM. And these days, and as we'll see, I've been working with a lot of the acronyms along the bottom there. So interplanetary file system, elliptic curve cryptography, conflict resistance data types, and Bloom clocks, which we'll touch on throughout this presentation. So things that we're going to be covering today, again, in broad strokes, content addressing as a concept, the potential for a global file system, user-controlled auth, so that's both authorization and authentication, and portable compute. Yes, this is all built FP style. So our server and CLI are both in Haskell. The majority of the web apps that we're doing first party are in Elm, including the OAuth style, but still user controlled auth page and the file explorer. The browser SDK itself, because everything needs to be compatible with JavaScript if we're going to have a large number of people use it, is in FP flavored TypeScript. And then we also have a responsive image resizer done in Rust, both because it needs to run native and in WebAssembly. We also have stickers. If you like any of these stickers, drop me a line after, and we will make sure those get to you. The ones that are probably of most interest to this group are along the left-hand side. So the Haskell Wizard and Lizards and Because Math as well. And if you're not familiar with the Streaming Snake case, definitely look it up. That is our very vaporwave version of that. So a little bit of background context on the kinds of problems that we're solving. Backends and DevOps are both really complex these days. DevOps in particular, it's now become its own specialty with its own set of tools that if I just want to get a website up and running or a web app up and running, I can do all of my development locally. And then I have to learn this entire other tool chain just to get it online, right? It's a much higher barrier to entry than it really needs to be. And even with things like Docker, learning to adjust a Docker image, there's a lot of sharp corners on that. And if we look at these sort of trends, it really feels like we're at or around peak Kubernetes, and people are already starting to look at other solutions more seriously, like Nix, which is again very FP influenced for reproducible builds, which is something that not even Docker containers have. For backends, the constraints really are that we're in this multi-tenant system where we're going to, as the app developer, we're going to own all the data. So we have to control who has access to what and who has a view of what things in our database. To maintain higher concurrency, we can either scale vertically with more powerful performance tools like Haskell or Rust, or scale horizontally, or what's becoming more and more common is sharding your system and using microservices. There have been lots and lots of data leaks, and even Apple recently had a major bug in their OAuth implementation that would let you log in as literally anybody, right? So it's very easy to do things wrong, even if you're a large, big co with a big team. And a lot of that is around access control complexity. And this meetup being in Europe, GDPR is a real big concern, because you want to make sure that even just for purely ethical reasons, you want to make sure everybody's data is secure and you're collecting as little as possible and not surveilling your users. But GDPR, a lot of companies are fairly stressed about being compliant and how am I sure I'm compliant? So we're trying to make all of these things, doing the right thing the easy thing, so that just by default these things are just taken care of. And this is, sorry, I did them backwards, but Docker, as this really coarse-grained idea as well, is to basically say, I'm going to take my entire machine, my OS, all of the dependencies in it, everything, and then ship that entire container, and we'll only have this sort of OS level granularity, right? So we took a step back and we looked at, what are the trends over time, and what are the things that must stick around and the things that we can get rid of. So first insight, front is never going away, right? You have to have a UI. You can't get around that unless you're doing purely, generating reports on a backend, right? But even then, you need a UI of some kind. Browsers continue to get more powerful, and we keep baking more stuff into browsers, even though a lot of these features have less adoption, I think purely by virtue of just being newer. So WebAssembly in particular is very, very exciting. It runs also outside of browsers. So we have almost like that 90s Java promise of write once, run everywhere. Well, we now have a pretty sane, well-built VM spec with multiple implementations that we can run in the browser, at the edge, or elsewhere. And there is also this trend from going from this large container down more and more granular. So what if we take that to the far extreme? So instead of just having AWS Lambda or something like that, we can get to edge computing, and from there directly down into Wasm modules, or further right down into your app. And how can we use these things to empower developers to not need a backend or learn DevOps, and maybe have some new, as we're evolving patterns and techniques, the techniques that we're using today are not the techniques we're going to be using in 2050. So what are the ways that we can get to 2050 in sort of an iterative way without throwing out everything and building towards this easier future? The constraints that we've set are really primarily around usability. So everything has to work directly in a browser, the same browsers that you can run Gmail with. So that's the latest 2 browsers for each of the major ones to get 99 some odd percent user coverage without a plugin. So we're not installing anything additional. The end user shouldn't be aware that anything different is happening. It should feel very standard to them. We have to have as secure or better than today's infrastructure, with equal or easier UX, so removing big chunks out of this, where users fully control their data rather than companies, has to work offline, and be infrastructure agnostic. So you should be able to run a production website directly from your laptop at a regular domain name, or deploy that to traditional infrastructure. It shouldn't matter, right? And then that little animation off to the side is us running a website directly from and deploying directly from a laptop, and making that available directly with our little CLI tool. This is possible because we have some new building blocks. So again, new things in the browser, and then some new concepts, content addressing, UCANs, or basically a adaptation of macaroons, and spooky auth, which was a concept from the 90s, which we're going to cover, CRDTs, and then most importantly, for all the things that we're talking about, immutable, i.e. functional data structures that we can now put at web scale and network together to say that everyone's data structure can refer to anyone else's. The sort of model to think about this is just like how one of the main things that people get confused about when we're describing this is, well, but how do I do things like I do them today? How am I going to aggregate user data, things like that, right? And the model's a little different. The way that we're working with this is more like a native app where you have this data substrate, i.e. disk, and authentication and compute resources and all of that. And you'll have a, say Photoshop, you put, it asks, hey, do you want to have access to your photos folder? Yes, Photoshop, you edit your photo, and then you go over to a different app and you can post it. And you don't have to upload the same photo multiple times. It's just talking to the same underlying system. We're making that same idea work for the web. And we'll start getting to the meatier stuff in a moment here, but the upshot of all of this is instead of having to scale linearly or manage complexity of many moving pieces, it actually scales sublinearly with some of our technical choices. So the more people hitting your website, actually it'll improve performance. The worst case scenario is how it works today, right? So we're having an exponential performance improvement. We can serve areas that don't have cloud infrastructure, like parts of Asia or Africa. Anyone can be a service provider. So literally your laptop can be a server, or maybe you wire up a bunch of Raspberry Pis, right? It literally doesn't matter. We can move compute to data and data to compute and run them, because again, everything's stateless in this functional model. It doesn't matter where things are happening. It just matters that we have an input and a known output, and we can run that multiple times and we'll always get the same result. So we can move functions around as data. And you should be able to get on a plane, no Wi-Fi, build an entire app, be the first user of the app, register, be the first user of the app as if it was in production. And as soon as you get off the plane and connect to Wi-Fi, it's all available, and all the changes that you made as a user of the system are real live production use. So let's talk about content addressing first. The underlying technology that we're using is called the Interplanetary File System, which is a totally separate project, but it works in browsers directly. It downloads and runs a web worker, and you can also run it natively. But there's nothing about what we're doing with it that is actually dependent on IPFS per se, but we do depend on content addressing as a concept. So the basic idea is we take some data and we hash it down and we get some string, and that string is the identifier for that data. So if you do this or I do this, it's the same hash, right? And we can retrieve that back. It works for more than text, right? So this is their standard cat image that you can download using its content address as well. Right, so it works for any data of really any size. I don't actually think that there's a limit. It's an arbitrarily sized data. You can represent the entire contents of a computer, including storage and RAM, all of that with a single hash, or an empty string, and everything in between. So location addressing is what we have today, how the internet runs. And it's really designed around server client and the single source idea, where you have, I want this photo and it lives on a particular computer and only that computer. And this works a little bit like a key value store, right? We have an IP address and some path at that IP address, and then the content inside that, right? And this is location addressing, but with names, with DNS. it's really focused on the physical network and routing, right? We have physical location is the basic layer, and then this virtual address on top, you know, an IP address, and then, you know, DNS just to give us a human readable name. And it works pretty well, right? It's how the entire internet works, but it's also mutable. So if I go to foo.com/baz today, that might be some JSON. Tomorrow might be a video. It could be an image of, you know, a screenshot of this presentation, or it might be with altered content, right? Like, we're not sure. We don't actually know. Content addressing or content IDs are one level of abstraction above this, where we, instead of saying that there's something that lives at this particular address that has then this path within it, which is almost like writing on an envelope, right? That there's this physical address. We have this universal relationship between content and its ID. So we hash the content. Let's say we take a SHA of the content, and that's going to be our identifier. And if I hash it or you hash it, or we hash it 10 years from now, we'll always get back that same identifier. We then go out to the network and say, hey, who has this content? And whoever then has it, it doesn't have to be on a particular machine. Anyone who has it, who's closest to you, will send you that. It's focused on the data rather than on the literal physical layer, the infrastructure. So we don't have to care where it lives. And the same data can live in multiple places or be in multiple paths. So we still have paths, which we'll look at, I believe, next. But we can't have cycles in that, right? We can't have loops. It has to be a directed acyclic graph. If we had loops, there's no way to construct that, because the data structure now needs to know what the hash of that graph is. And if we don't know, like, if there's a cycle, then we're always going to be changing the contents of it. So it's you know, conceptually possible, but not not practically feasible. You can't actually do this. Here's what linked data looks like in this model. So we have, yes?
Yeah, someone is asking about hash collisions.
Yes, so technically possible, but the size of these hashes is so large that it would, the probability of that happening is extremely, extremely low. It may happen over the course of, you know, the order of thousands of years. We may have one hash collision. When you look at the actual size of the hash space for these 256 bits hashes, it's really, like, you know, more than the number of atoms in, you know, the known universe kind of thing, right? It's like huge, huge, huge space. And most of those hashes don't point at something useful, right? They would just be sort of garbage files. So generating two hashes that will collide is possible, but highly, highly, highly unlikely. But really good question. Are there more questions, or should I continue?
Jump in very quickly and ask one.
Yes.
And I don't see any, so please continue.
All right, great. So linked data. It's represented with essentially a JSON structure. That light blue in the top left is the hash that points at this structure. And we say we have some data, it just is hello world, and some links off of it. So I'll have company and license, for example, which then have in there other hashes, which point to a similarly structured piece of data that also has further links. So if I have that top hash, then I can use that to address within it further items. So we can still have nice readable paths. We can also stick that top hash directly in DNS in a text record and have a fully human readable name. So we're able to do, you know, mycoolapp.com/about. slash, company image.jpg, and that will resolve to an actual image. The thing that we get out of that is you can always look at the text record, both verify that the content is the content that it claims to be, because we can hash everything and make sure that nothing's been tampered with. And at a later date, if I want to get the older version, I can still go back and get that. In fact, in our file system, we're keeping everything versioned. So it's not just a tree, it's a versions tree, so that we always have pointers back in time. We get, so these links also work within files. Everything's broken down into blocks, so smaller chunks. And if two files have the same content, we can deduplicate it and point at the same block. So we actually get some limited amount of compression as well, which means that a lot of these chunks will be available and around if it's a popular file or if it's a version of a file that has already existed. The actual lookup works out well for our goals. So you're going to look up a file, and the first thing you're going to do is look on your machine. Do I already have a copy of this? And if you don't, then you'll look at your direct peers. So you might be in a coffee shop and have one of your friends nearby, or you'll discover somebody over the router, and they've been looking at a popular website recently that you're asking for, and they'll just serve it to you directly with very, very low latency, right? This is the extreme of edge computing, where the person's sitting next to you. This also works over protocols that aren't HTTP, but for now, we'll just keep it on an internet version. Now, if they don't have it, we go out to the broader network, to the actual internet, and we say, hey, who has this? These highlighted machines are the ones that do. We get routed to them through discovery. It's actually usually only 1 or 2 leaps, just because of how networks work. The number of links increases with the square of the number of participants. And while it's not evenly distributed, you can generally get to a hub very quickly. So it's on those machines, we drop everybody else, and then we torrent it in parallel from multiple sources, whoever has it. So beyond just having, we've moved up to HTTP2, where we're no longer doing, blocking of header blocking. We can actually torrent all assets on the internet. This also provides a single namespace for absolutely everything. We just have these content addresses. Yeah, we can stick things in DNS to get human readable names, but this content addressing is universal and can describe absolutely anything that's data, right? Each node, so every computer, browser, server, will have 0 file duplication. So if 3 people ask, for example, our service to keep something online for them, the same image, we only have to store it once. And same thing, if you go to 5 websites on your laptop that all have the same photo on it, you're not going to download and cache that 5 times because they have different file names. You're going to get the same file and cache. Replication, just like the routing prior, we get CDN-like features where popular content is automatically distributed across the network, and people can serve it to you, very nearby. All of the data structures are immutable. That doesn't mean that we can't change or append things to the head of the data structure, but it's immutable in the same way that say a closure data structure is, where we have a pointer to some item, and then we can have other pointers to it, and even drop it from the head of whatever we're doing, but that hash is still around as long as somebody has it. We can also do structural sharing, where we're let's say that there's 2 trees and they only differ by 1 file. Then we can deduplicate the shared files by just having these pointers. Files and data are the same thing. So if you have some in-memory data structure, we can also content address that as long as we can serialize it, or even just as binary. So you content address that. You can content address databases, transaction logs, and full files. Doesn't matter. So we're using this to both do a database to both do a file system, traditional file system, but also to do a database and to handle CRDTs for live interaction as well. And there's a number of different projects doing full databases on top of content-addressed systems. We know that we're going to have to go and build a full-blown database at some stage, but as we'll get into in a little bit, we don't need to have this multi-tenant assumption because we don't have a single server that everything's running on. We're assuming that everybody has their own shard. So the 90% use case is no longer everybody needs to be in the same database. We can have everybody maintain their own database, which radically simplifies that design. And you no longer need as much power from something like SQL, right? You only store the data that you care about in almost like a GraphQL cache. Fission file system is exactly what it sounds like, Unix file interface available in the browser or on your desktop. You can have the same files across all Fission powered apps underneath. So again, more like a native app than a traditional web app, where an app will ask for access to your file system and then you grant it or not. It's fully immutable and a temporal data structure. So temporal data structures are there's a few different variants. We're using a functional type where everything's completely immutable. You always have pointers back. So every directory has a pointer back in time, which then will propagate up as well to say the contents of the root of your file system has also changed, right? Lets you go and peek back in time and say, oh, what was the state of this file 3 weeks ago? Or you can roll back, which is really peeking and then making a copy of that and linking it in front of where you are now. So everything is completely non-destructive. You lose nothing. It's all event sourced, so you could write an app that consumes the event stream off your file system and processes that in interesting ways, gives you stats or produces an RSS feed, etc. You can take a directory of songs and say, this is now a playlist, or this is now my podcast. It's broken into two sides, and we'll talk about access control in a moment, but there's a fully public side and then a private side that's fully encrypted and that the user has granular access to grant both read and write permissions to. This is the Elm UI I was talking about before, and there's, for those who were on prior to the call, Boris was piping up. That's Boris getting excited about some ice cream. And this is Boris's file system on drive.fission.codes. You can see there's directories and photos and all of this, and that lives directly in the browser. And there's a private side of these files where he can grant access to only certain people or have this public version. And not just photos, we can also have, as you deploy apps, also the source or the build folder as well, accessible directly in here. In addition to being able to launch apps in a traditional, just instead of going through this interface, just go directly to a web page way. So access control, I've mentioned a few times, fully without a server, client-side, user-controlled authentication and authorization, powered fully by the browser. So first problem, how do you do user IDs without a database? Well, good news is that there's already standards for this. So we're tapping into those. And these are not, sort of 10 years from now standards. They're being worked on heavily by, Microsoft and other big cos, as well as W3C standard. British Columbia, which is the province in Canada where I live, also has a project for these as well. These are called decentralized IDs, DIDs. You can assign them to user devices and more, and they're based on public-private key pairs. So the public key is your identity, and the private key, you can sign messages with it to prove that you have control over the public key. So it's the same way that you do SSL or, say, doing signed commits on GitHub, which if you're not doing, highly recommend, it's a good idea. because we can generate these on the fly, anyone can create their own ID, and it's a truly universal UUID because, again, the namespace here is just massive, right? And it's agnostic about the backing. You can still keep these in a database if you want to, or give it to a third party or a blockchain, or what we're doing is literally just using the Web Crypto API, keeping the keys in the browser in a way that no one has access to the private key directly, but the user can make requests to it and approve actions. The security model for Web Crypto is actually pretty good, even though it's a little bit limited. The other nice thing is it's totally self-sovereign. So beyond it working offline, as long as you're in the browser, you can create as many of these as you want. You can have pseudo-anonymity if you want or not. You can also build up, say, reputation. People know that this ID is me, or stick it directly in. So when you sign up for a Fission account, we also give people a username, and we stick a text record with did.username.fission.name, where people can go and look up your public key. And by people, really, I mean programs, because humans don't care as much. We sometimes need to verify that you're allowed to do certain things or that you're you, and so we need the public key somehow. There are many methods of this. We're using the simplest one, which is just directly, it's a public-private key pair. We don't care about anything else. And this is what that string looks like. So we have this DID key, Z, and then a long random string, which when we decode it, this is an elliptic curve public key. So this is quantum resistant, military grade security for a key pair. And it runs in our tests sort of in the range of 20 to 80 times faster than an RSA key, just because basically the math is a little bit slicker. There's a few different methods. We also have RSA keys, which are the ones that most people are familiar with, in there as well, just because it's so commonly used. But we have really noticed a major improvement with these elliptic curves. So that's how you identify somebody. How do we do read control in here? So there's two models for access control. One is ACLs, which is pretty much how we're all used to it. It's how it works on a Unix system or in most auth. The other is object capability model, or OCAP. If you have a Elixir or Erlang background or anything with the actor model, it's actually pretty similar, where you have proactive access control, where you have some proof that you're allowed to do to do things. So in the actor model, you either have a process ID, you know how to talk to the process, or you don't. In this case, you either have the key that you say you do, and you can sign a message with it, or you don't. So we don't have to maintain an entire rules hierarchy. We hand out keys. We can give do key exchange. So if you have a public-private key pair, we can then give somebody this shared key in an encrypted way that's only for them. And if we want to revoke access, we change the key and hand out the keys again in a way that the program can look it up later. And these are just normal, they're called AES keys. They're sort of the standard. They're very fast. They're what's required, again, for top secret security with the US government. So they're sort of the gold standard of security. To give granular access to something in this file system that we're talking about, we use a technique called crypt trees, which is one of the really nice things about having this immutable data structure as a file system. So if we want to give access to this region here, the red region, we encrypt that directory and all of its contents underneath it, and then hand the key to that. And then we want to go up another level. Okay, well, we'll have another key for that as well. So what we do is for every file and every directory, it has its own key that inside has keys for everything underneath it. So the root, if you give somebody root access, the expected user experience is that you should be able to see all subdirectories. This is how Dropbox works, or Google Drive, all of these. But if you only want to give them access to a project folder, you only give them that one key. They can't see anything above it. They can only see things below it. You later want to revoke access. You change the keys. You re-encrypt everything. It's a fairly lightweight process. The main thing that you need to encrypt is the file index, so that they can't then find those files. So you can do the actual file encryption offline, out of band, and then redistribute the keys to the people whose IDs you know, which we can do with a technique called key exchange. So this is a recursive security model using these keys and recursively encrypting each directory all the way till we get to the root. And again, fully user controlled. So it's not that us Fission have access to this at all. In fact, by default, we don't have any access to anybody's data. We'll back it up for you if you want us to, but you don't have to. And the user then hands out who they want to have access. So not even apps have access unless the user grants them permission. Delegated write access is yet another model. So in OAuth, it looks a lot like this system on the left, right? Where you ask for, hey, am I allowed to have access? Then you get a grant token from an authorization server, which you hand to the application, which then talks to the auth server, which then gives it an actual token that it can talk to the resource server with, double check it, and then give the resource to, which is a lot of flow. We use, again, just cryptography to prove that you're who you say you are. And instead of asking an authorization server for a token, you, the user, can generate just a regular JSON web token, a JWT yourself that says, I grant this other user who has access to this public key these rights to write to my file system to such and such a directory. And that radically simplifies the flow, right? So instead of having, I think this is 11 or so steps, we have 4. And beyond that, if you delegate, so let's say I give access to Stephen to write into my file system, but then he needs an app to also write into it, he can turn around and redelegate some subset of his access, so the same level or less, for the same amount or less time, to somebody else, to another service. Yeah, so to literally anyone else. So it might be used to link devices together, or to give access to another user, or to an app, right? And sort of like a traditional server. Those proofs are nested. So we borrowed this idea largely from Google, actually. They have a system called macaroons, which is, and this is a terrible pun, but stacked cookies, where you have some root proof, and then you wrap it in another proof and sign that wrapper, including the root. And you do this as you go out and out and out, and each layer is allowed to have some subset of access, and it proves it by having access to its previous version. They do this still with servers, and they're using this to solve the problem of, instead of having a single authorization server getting pelted with Google's level of requests, they hand out to different servers one wrapped level of delegation, and then those can go and do whatever they need, for users, and have it more distributed. We took that to the far other extreme and said, well, we've equipped all of our users with a key pair, so they can be the quote root server and do this themselves. So we don't need a root server at all. This works offline. And again, it's a universal in the sense that it works regardless of time, place, or user, as long as you have access to those keys. And this is what one of them actually looks like. So in very sort of concrete terms, it's a JWT. This is this particular one's an RSA one, but works with any of the JWT methods. This is our issuer, which is a DID. And here's our scope and potency, so what you're allowed to do with it. So this is, I'm going to allow them to only append new stuff, not delete anything, to my public photos, right? Pretty straightforward. And then we're going to sign the JWT in the same way that we sign any JWT. The difference is this is a self-signed certificate rather than coming off of a server somewhere. The challenge is that the proof, which is another one of these, if we do 2, 3 levels of that, that actually gets quite large. So the solution is to content address that. And now we have just the hash inside and just for transmission. And so if then they make another request to alter some data, and you've seen that proof before, you don't have to go and pull it again, right? We have caching enabled. And then finally, portable compute. So this is forward-looking. This is something that we don't actually have yet, but I'm really chomping at the bit to get to. This is the thing that I really want to work on, but the rest of this is supporting pieces. It's called portable compute, where if we live in this functional world, it doesn't matter where the compute happens, if it happens in your browser or on a powerful server somewhere. So we can have dynamic functions as a service. So think AWS Lambda, but works everywhere, including on your machine offline, or if you need extra power, you can push it out to some service provider with a heavy compute workload. Everything runs locally by default. So if you're doing development work or you're offline, everything still works. And this is great for people with powerful machines, but if, say, somebody has a Chromebook, some things might take a while to run, or if you're running a machine learning something, if you're on a powerful desktop, then that's great. But on a laptop, you might want to push that off somewhere. So dynamically at runtime, we can determine, I want this to run locally or remotely. We have a couple different techniques for determining what that is. One is to tag some section of code as this needs to run remotely if possible. Or in the case of total functions, we can do some complexity analysis ahead of time and say, hey, this is something that will hit some threshold, the field's called cost dynamics. So we're going to hit a certain cost, so push that off somewhere else, which is really great. We can take anything that's heavily parallel as well and push this off into multiple different service providers and then collect the results back. The other nice thing that we can do as service providers is do arbitrage on compute. So if I've seen, actually, this might be on the next slide. Yeah, oops. So if I've seen some piece of data before or a function before, and I've seen them together, I don't have to recompute it. I can just pull it out of cache. Because code is data, right? We have to serialize it to push it over the wire. And we can memoize arguments, and every piece of data is content addressable. I can hash the function and then add the first argument, hash that, add the next argument, just currying, right? And if I ever hit some point in computing, some function where I hit a content address I've seen before, I don't have to keep computing, I can just grab it out of cache. This is applying hotspot optimization at web scale, right? This is a world computer now. We can take, the trade-off is that you're now pushing things over the network. So instead of running something locally, you have to contend with latency. So the question is, at what point do you hit that trade-off, right? It only works on a restricted subset, so total functions, which we'll talk about directly after this, how that works. There are a couple ways of doing this. The three most popular are a total subset, which I've seen in the wild, a few companies trying to do, our event-based two-phase commit approach, or fully trusted, i.e. run something in AWS Lambda, because you can, right? You won't get the caching, but you can still run things and push jobs out that way. So the completely total approach, which I definitely see the appeal of, is you have pure functions and side effects. Pure functions, you make some requests, the functions run, you get the result back, and then you make a separate kind of request if you want side effects. So I want to actually, post this image to Twitter, right? Then you need to push that out. The two-phase commit, or the event-based option, is nice because it also works with CRDTs. So we can have events that we can replay that can even come in out of order, and everything will still work. So you have your base event stream, a pure functional stream, platform effects, things like writing to a database, and then off-platform side effects. And if anybody's done Haskell, this probably looks familiar thinking about effects, right? So the purely functional stream totally works as you'd expect. You want to do off-platform side effects. This is, again, two-phase. You'll post the image to Twitter, and then you'll get a response back that says, yes, this was posted at such a time. Here's the confirmation. And we write that back into the stream so that if we're replaying these events again, we don't post to Twitter again. And the really interesting one is on-platform effects. So I want to write something into a database, a shared database with other people, right? So I can, make the request, get the response back. We write back into the log that this happened. But if I need to go back and replay over my events, or I've pulled down the event log and I want to reconstruct the state, I can skip an event if it was a bad one. Whoop. I think I hit the wrong button. Yeah, I can skip the event, or we can go back and wipe over it as if it never happened. So every part of this is very, very flexible. If you pass this off to a service provider and they give you the wrong result, you can wipe that result, put in the correct one, and keep moving. So as a recap, you can now build and use locally apps. Everything that you can run local on your machine is production. Or you can also have replicated versions of that where some replication is AWS or DigitalOcean or wherever. There's no such concept as deployment anymore, so we don't have to worry about packaging it up and all of that. It's just literally a web app. Zero config required. You just push and it's done, and everything else is handled in an SDK. We only serve the app, not the data by default, because users can grab their own data, which they likely have already on disk, but they can also grab over the network. And we're very efficient with bandwidth because we have all of this deduplication, and everything is capable of running locally on machine. For the user side, you have one identity for all services. You can generate new identities as you need. Client-side auth that doesn't require the network. Literally military-grade security, which is very much, I think, a nice to have for people. People say that they want it, but only if it's convenient. So trying to make that very convenient. User-owned data, GDPR compliance. Share nothing unless you give them access to do it. Dynamic functions as a service, and offline first, and local network enabled. And that is, yeah, I guess we have 2 hours, which is great. So that's 1 hour of it. And a few links there, our website, our forum, and we have a Discord as well, and a newsletter, which is on the website too. So that's the gist of it. And I'd love to hear people's questions or comments or even points of clarification.
Thank you, Brooke. That was super interesting. I just don't believe any of it. Seems like too good to be true.
Yeah, well, we have a long way to go first.
Have you heard of Unison by any chance? What Runar's been working on?
Yeah, so I've heard of it, looked at it briefly. I like the general concept. It's very aligned with what we're doing, for sure. Content addressed code totally makes sense. Yeah, there's definitely some overlap, for sure.
Yeah, I'm just into content addressed everything these days. Seems like such a powerful tool.
Yeah, extremely powerful. Yeah, so we're almost more focused on the data, and they're almost more focused on compute. So as both these projects become more mature, you can definitely see it having some overlap. And maybe we can do a unison integration at some stage.
Yeah, no, that'd be great. I'm actually curious myself to know which parts of this have you been kind of innovating in-house, and how much of it would you say is like best practices that have been like out there but just haven't been integrated together in the way that you're doing?
Yeah, so there's the old saying that nothing's new. Even stuff that we innovate from first principles, we then later find, oh, there was a spec for this from the 90s, right? So we're really aiming at making best practices easy, data security, highly scalable, all of that stuff, which is really informed by traditional web best practices. And we can't innovate on everything. Most of our innovation is plugging existing ideas together in what I hope is an interesting way. But we haven't done never roll your own cryptography, right? So we use things that are already built into browsers. We look at what Google's doing with auth and adapt it. And then later discover, oh, there's not exactly the same thing, but actually pretty close from the 90s called SPKAI or Spooky auth. That's like, oh, well, we're almost like a blend of the two. So it's really this adapting approach.
Do you have an example of something that you kind of discovered along the way that you then went ahead and implemented or integrated?
I mean, many things. It's pretty R&D heavy, as you can imagine. Yeah, so definitely, I mean, a lot of the stuff around the cryptography has been a interesting learning experience / discovering what's possible. And a lot of the web APIs, like there's honestly so much available in all the standard browsers today that I just didn't even know existed a year ago. WebAuthn, being able to authenticate stuff with your fingerprint on a Mac or with your face on a Surface, baked right into browsers now. It's pretty limited, like extremely limited to certain use cases, but I didn't know that was a thing, right? You can do passwordless auth right in the browser with key management that will never get cleared by freeing up cache space. It's pretty amazing. And then, yeah, I mean, like there's a huge number of smaller things. Temporal data structures, which I'd been aware of prior, but more for like a purely academic interest, is now like, oh, right. We can do not just crypt trees, but we can also make them fully non-destructive because we already have deduplication. So let's use structural sharing in this new way to basically have time machine in the browser, right? So again, it's still same answer, I guess, is it's all adapting things.
Okay, so I just have one last question right now, just because I'm curious. What is your product? Exactly.
Yeah, so we're giving people. So the underlying question is, what's the thing that we make money from, right?
Yeah. I don't want to be so crass, but
Yeah.
Just curious.
So it's a excellent question, and something that I think everyone should be asking companies. So yeah, we're giving people these tools to do things completely in the browser or on their desktop without needing a third party. Yet we're a third party. We're providing convenience. So if you are hosting a website directly from your laptop and you close your laptop, your site's gone down. So you want to have a replication of it somewhere. So somebody might have looked at it recently and now they have a copy, but we can do the backup for you, right? Or domain names, right? You want to release an app, you have your whole release pipeline, which we're integrating to the CLI right now. But at the end, you don't want mycoolapp.fission.app, you want mycoolapp.com. We can sell domain names directly from the CLI. So you don't have to use us for those things. And in fact, all of the services that we're providing, from the original Sweden slides, I've removed the more philosophical section on by having more people compatible with this way of working and even competing with us for hosting, let's say, that lowers our burden for hosting data for people that decide to use us, because we have this whole content addressed network. So by competing, they're lowering our costs, right? So we're basically winning on efficiency and convenience, basically, or hoping to win.
Okay, I'm rooting for you.
Thanks.
So I want to invite everybody who is still with us to put your questions into chat. I hope you can ask some interesting questions to make our wonderful speaker feel welcome. I'm a big believer in questions. Robin has a question. So Robin, do you want to go ahead and unmute and ask your question?
Sure. So you talked about carrier functions partially applied, and so I can understand if you have a function and you look that up and that's cached, you can get some JavaScript or something. But how would it be if you had a function applied to one argument that is expecting another argument? What are you actually looking at there?
At the content address. So we take the function itself, hash it, and then say, for every single argument, if one of the arguments inside is say a higher order function, you mean, and then that's expecting arguments as well?
No, I was just thinking in terms of if it's a 2-argument function, but you're saying it's carried. So if we've said, I recognize this function applied to the first argument.
Yes. What
are you actually getting back from the cache there?
Yeah, so this is assumes WebAssembly. You can do this with JavaScript too, but it's messier. V8 actually is now, I believe, WebAssembly underneath. But so WebAssembly is a fully deterministic, or as much as they can be. They're trying very hard. Virtual machine, and so we can take the as we're running the machine, the progress that we get to, freeze that state, and keep it. So if I've now seen the same function with the same, say, first argument, but different second argument, say, I don't know, we'll put a counter on it 10 times, then I know that when I make progress as far as I can, reducing down in the function, then I'm going to try to make as much progress as I can, and then I can always resume that later. If we're using the second argument first, let's say, we can still skip that and try to reduce all of the, say, if there's any equations or things that need just the first argument inside there. So yeah, basically taking the larger problem and making it into a smaller, more specialized version. So this is how, if you're familiar with Java or the JVM, has a hotspot optimization. This is what it does. It basically says, oh, I've seen the same argument X times. I should make a specialized version of this that's faster.
All right, that's really awesome. Yeah. It sounds a bit like partial evaluation. Is that something that that is done by the VM, or is it something that you've introduced?
So there, I know of WebAssembly hotspot optimized runtimes, but if we're going to do this over the web, even with some sections, so we, with the portable compute, we should be able to take a function, and let's just say the more magical version where we're doing the static analysis ahead of time, right? That we know that something's going to be long running. I should be able to push that out to the network, ask, hey, could somebody run this for me faster? Or if you have the response, I don't care, just give me something faster. And then return that sub-computation, that subroutine, basically, that closure response back. that isn't baked into Wasm because it's not network aware currently.
Okay, I guess we can move on. Let's see, Thor has a question. Thor, do you want to unmute and ask your question?
Yes, thanks for the presentation. So I was just wondering in the chat there, you talked about, there being hubs for a particular piece of content or logic. But so let's say I'm a software company and I want to launch my app and I have servers, I have money to pay for servers. Do I just are they just highly powered, large store space peers to the rest? Do I just install the same software there? Like, what's the story there? Like, even though there's no kind of formal differentiation between user and server, what's the story there, I guess?
Yeah, so another excellent question. The way that you start, so we're moving in this model away from client server towards something that looks more peer-to-peer. But not all peers are equally powerful, right? So if I have a server rack at home for my own personal use, or if it's sitting on a heavy duty server somewhere, managed, it shouldn't matter. So I sometimes jokingly say some peers are more pure than others. You basically have a very powerful peer that will, that is online for a more persistent amount of time than a browser tends to be, or say a mobile device, that will probably be discovered through routing, more other peers, and start serving requests to more people than, say, my mobile phone will.
And does that just happen transparently because it has more power and capacity?
It happens more due to the length of time that it's online and the number of requests it can serve. So the network will become aware that, oh, this is someone that we all have the address for and we all know about, and that hasn't failed me in the past, so I'm going to make lots of requests to this peer.
So, and is that just a matter of, on this computer or the server, there's going to be a user, you make use of all the cores, but it's essentially just the same thing. It's running, a similar kind of stack, I suppose, that the person on the laptop would be using.
Yeah. So so for example, our sort of hosted platform is one of these, just call it a super peer for now. And we run the same, a different implementation, but of the same software that runs inside the browser, right? So we're using IPFS as this base storage layer. It can run, there's JS IPFS that will run anywhere. And we run Go IPFS, which is the other official, or I guess it's the main implementation is in Go, and then there's a JS one that also runs in the browser. So our server runs Go IPFS, but that's fully compatible with JS IPFS. They're spec first and then implementation later.
So I guess this automatically takes care of things like load balancing and availability, whatever. Like if it's not there, it's not there.
Yeah, so the trade-off that we make with content addressing is we don't know. So I know that on this machine, I don't have this file, but I don't know if any of my peers don't have it. So you can, if you set the timeout to forever, you'll wait around forever until it becomes available, right? More realistically, you'll put some time limit on it of like, well, if it's not found in the next 5-10 seconds, just give me a 404, right? Yeah.
I'm just wondering if there's a, how much more complexity do you think there would be in like running this kind of server farm type thing? Is it?
So actually very, very little. So it's not that you have load balancing and in quite the same way as you would on traditional infra. IPFS maintains something called a want list. So it says, oh, I've heard from so-and-so that they want hash ABCDEF. So I'm going to let everybody that I know that I want that same thing, but I'm not going to keep a connection open or wait for it. I'm just going to leave this here until somebody responds with it. So it's totally non-blocking. We don't have to maintain persistent connections. We just say, here's something on my list, and then when I get it, I remove it from my list.
This is very cool. Thanks.
Yeah, yeah.
Thank you. KK has a question, and KK's mic is working today.
Hey, thanks. Hey, Brooke.
Hi.
Yeah, in the earlier part of the talk, you mentioned lots of stuff about the content addressable stuff. I'm just wondering how much of that is already provided by IPFS and how much of it is new stuff that you've developed? Yeah,
so the actual content addressing, we're just using IPFS. IPFS itself is a collection of sub-projects. The main one being the routing. The actual content addresses themselves are just, well, it's actually self-described in the hash, but it's just a SHA hash of the content. So if you have something that's capable of SHAing some data, then you can create the address. The actual looking up of that address relies on something called libp2p, which is made by the same people. And together, you know, this whole stack together, and there's maybe 3 or 4 other major pieces of work in there, plus some standards, is how we get the whole full networking stack. So it's actually nice that it's so decomposed. We also have things like PubSub in there, and a few other things that other projects have taken and are using separately from IPFS as well. So it's nice that it's done in this nice granular way. But
cool, thank you.
Maybe to the direct question, are we adding anything ourselves to the content addressing layer? And the answer is no, we're using something off the shelf. But we're also not totally coupled to IPFS per se. It's just a fairly mature or mature enough implementation for us to use, and that has enough other peers to actually form a pretty robust network.
Great, thank you. Yeah, cheers.
Yeah.
So next we have friend of the meetup, David Chambers. David actually gave one of the earliest talks to our meetup. I don't know if he remembers. I think it was 3 years ago and in person. So David, do you want to unmute and ask your question to Brooke?
Sure. Yeah, my question is, what do you mean by FP-friendly TypeScript?
Yes. Or I guess FP flavored, maybe. So with TypeScript, you're really just given, on top of JavaScript, types. And types can also be used to describe, say, a fully object-oriented style. Not that OO and FP are completely opposed, but you can use it to describe this more imperative style programming as well. We're using it in a very FP stateless transformations on data structures way, mainly because, both for preference of style, but also because that that keeping everything really scoped keeps things very flexible and easy to use in even an imperative style as well. But then we can also use it in the full FP environment too.
Were you using any libraries to make that easier?
No, just okay. The main, just TypeScript. We're not using, say, a monadic interface or something. It's just transformations on data structures.
Cool, thanks.
Yeah.
So I don't see any other questions in the chat right this moment. Just in case people are wondering, which parts of this project, I'm not sure what to call it, project, application, system, wizardry, are you building with Haskell, and how has that been an advantage for you?
Mm-hmm. So Haskell server and the CLI tool, both. So basically all of the backend or native components. It's been an advantage mainly because small team, and we get a lot of leverage from this language. Everything's inside is described well. And we've had very few bugs on the server. All of the ones that we have had are around things like was there padding on the incoming string, things like that. Internal bugs to the application, I believe we've had next to none. So we don't have a ton of effort being thrown into fixing things. We write once and it's pretty solid after that. For the, what? This is my fault, suggestion. With the CLI, so we're using Servant as well for the server. So the CLI can consume the same types that the server puts out. And so we have a consistent interface between the two that's auto-generated, which is actually really nice that we don't have to worry about, did it break, right? They just stay in sync. We're also using it for document generation as well. So we have Swagger docs as well. And so as soon as we change part of the interface for the web portion, that automatically gets updated and reflected as well. Actually, all of our stuff is open source, or the few pieces that are not quite like the source for the Drive application is still closed, I think just for this week. We're almost at release for that, like a true 1.0. But everything else is open source. The server's open source, the CLI is open source. You can go and take a look at how we're doing it, trade-offs we've made. And, you know, this is Haskell being used at a, you know, it's myself and 2 other engineers. Small team in standard startup chaos. You know, you can look at an actual production system for a small team, not just, you know, the team at Facebook doing Haskell, and seeing the trade-offs. And sometimes it's like, yeah, you know, we need to just plow through this one particular thing, and it's described in types and not in text, and we want to get back to that, right? But it's still probably the cleanest project that I've worked on across any language, maybe, despite the small team and the speed that we're trying to move at.
Well, you answered my follow-up question, which was going to be about open source.
Oh, yes.
I could,
yeah.
Go ahead.
Oh, so yeah, open source. We have many opinions about licenses at Fission, but the server is Apache licensed, so other people can run it. They just can't, if they make changes to it, even if they're running it closed, they have to make those available as well. We want other people to run our server and lower our bandwidth costs, right? So it's interesting that the technical decisions and the network produce these almost, you know, these business level decisions and collaboration through competition, which is not a phrase I thought I was going to be saying, you know, 3 years ago.
I can imagine a follow-up talk could even be about your experience using Haskell in production in this environment. I think a lot of people claim that using typed languages, they often can't develop quickly enough, and they like the fast prototyping power of more dynamic languages. But it sounds like you're not having that problem at all, and in fact, you're leveraging Haskell's actual strengths and benefits to move quickly.
Yeah, so I'll give you sort of like the pros and cons that we bumped into. I fully don't buy the dynamic languages are easier to prototype in, because I have types and I can prototype my types first, right? And give it a simple implementation that doesn't talk to a database or anything, right? Because we tend to work from interface inwards, typically, right? Especially when producing things for other people to consume. So that is all typed. And yeah, we get to use it for its strengths. That it's not that, again, not that there are 0 bugs, there's few bugs. And the bugs are never things that are well described in our system. And when we're, again, with the exception of certain kinds of cryptography and character encoding, then we have a very high degree of certainty about what the assumptions were when this was written, and sort of the state of this piece of code, and having things be highly compositional because every piece can be isolated and snapped together, right? The downside has been, so I've actually been surprised at how little we've had to deal with an education burden with Haskell, because it's just so different. Part of that is, I think we hired well. So Steven van de Velde, one of the other engineers, already had a Haskell background. And Daniel had done a ton of TypeScript and Redux, and we could kind of bootstrap up that understanding actually surprisingly quickly. We had originally started, instead of with Elm, we had done a test with Reason. So he had already been exposed to a similar type system. So that actually went fairly smoothly. We did hire somebody else at one stage who really struggled with Haskell, and just, it never clicked, got really focused on it, and didn't, who had been a senior engineer elsewhere, and just really was struggling to be productive with it. So that didn't work out. Something I've noticed, so you had mentioned early on that you guys run a Haskell reading group. And so something that we used to run here in Vancouver too was Haskell from First Principles, like the book reading group. And we had, at its peak, I think like 45 or 50 people in different cohorts going through this. And typically people who were really, really experienced with, Ruby was one example, had a really hard time grokking concepts like laziness in Haskell. Like, but how do I call the function? You don't, it just happens, right? And so having that previous experience can sometimes hurt, because you have those deep grooves of experience, whereas people who are coming into it earlier in their career, everything is still new and fresh and difficult to some degree, and they're just more open to new ways of doing things. Not to say that it's impossible, but that's kind of been the trade-off that I've seen over time. Is sometimes it's hard to bring in people who are more experienced in a different stack.
Yeah, this comports with my experience as well. Not always, but sometimes, people who are coming from a place where they feel like they're an expert already. It can be very hard to give that up and admit your ignorance in order to learn something new. And it's true that people who don't know anything are often better students in a sense than seasoned programmers who already know some other stack with that, where they feel comfortable.
Yeah, exactly. The other thing too that I should probably mention in our specific case is it's a good filter for us, because we're doing all of this strange maybe future stuff where nothing is, you previous experience is good and useful, but not all of it applies, and you have to be very open to trying new things. And so coming into not a top 2 language can be a helpful filter.
Yeah, I just want to say that I started learning Haskell in my late 30s, so I'm as stuck in a rut as you could possibly be, and I managed to do it. I think just some people, I don't know, their brains seem to be set up for it. I don't know. I don't mean that in a sense that you have to be like intelligent in a certain way to get Haskell. It just seems to appeal to some people and not others. I don't know. I don't know how that works, but I found this to be the case in trying to explain it to people.
Yeah, there's a fairly old idea that, like, I mean, the world isn't this clear cut, right? But that there's sort of 3 personality types, right? Mathematicians, engineers, and linguists. Engineers are going to be drawn to C and Go and Rust, though Rust really bridges a lot of this, I think. Mathematician style will be a lot of FP, definitely the ML languages. And linguists are interested in, are interested more in things like Lisp and Racket, right? So you basically have people who are interested in the machine, people who are interested in the properties, and people who are interested in syntax and expression.
I hadn't heard that before. Okay, that's interesting. I have to think about where I fall in that, that spectrum.
It'll be some mix of the three, I think, but that's it's a breakdown.
Cool. So Boris wanted me to mention, Boris, your co-founder who is with us right now, that the license is AGPL, not Apache, for the open source stuff.
Yes, I got the wrong A license. So yeah, it's Apache 2. Sorry, AGPL, not Apache 2. AGPL specifically so that we can do the if it's run closed source or and then changes made, then you have to open those changes.
Okay, and Giri has 2 questions, and I'm not sure. Giri, would you like to ask either or both of them?
Yeah. I mean, I asked the second one, which is probably easier, but by the way, I've seen some of the slides before, and the presentation was just amazing. So I just wanted to say that I really enjoyed that, and it was much easier to follow than just reading the slides. So it was great.
Yes.
Thank you. So I really like the linked data idea, obviously. And now if you could make the assumption that all the data that is passed to anywhere, anytime, it's all just linked data of that form. If you could make that assumption and make whoever writes the application to do that thing for you, then of course the whole thing could be even more simpler. And it really would be like solid without the overhead and the burden of RDF jiggery-pokery. What would you think of that?
Yeah. So, and again, I'm going to adapt this answer a little bit to the FP meetup. So yeah, all data is linked to large degree. Yes, it's a nice way of describing relationships between data. Do I think that there will be and yes, for compatibility reasons, if you can have like a shared schema between multiple apps, yeah, that would be great. And we're basically saying, that the data will be of the same shape or the same type, right?
Yeah, I mean,
or at least subtype.
Right.
I don't, unfortunately, with the way that the world works and the incentives are set up, I don't believe that is an outcome, because as soon as you go from being the underdog to the incumbent, you try to close things off and prevent people from competing.
No, but the point is that the very idea of this linked data structure, as you described, that's completely open. There's nothing to add, nothing to take away. It just, how you use it. So in that sense, it is universal as is. It just requires universal adoption.
And that's the challenge. Yeah. So is the link in the schema? Yeah, but even with, say, Microsoft Word docs, right? They tried very hard to make those obscure and difficult to reverse engineer, which we eventually did. And yeah, this linked data will be out there and people can use it and adopt it. But if there's 10 different ways of doing a playlist, then your app either needs to support the 10 ways or use the subset of all 10 ways or pick one. And so part of the hypothesis, and again, we haven't actually built this part of the hypothesis is that most people are looking for convenience. So if we can provide common use cases for people, just bake it into the SDK, playlist.new, and it'll be in a particular format. And then same thing with photo albums and other things, then we can achieve a higher degree of compatibility between people building apps on top of the system. But again, I think if a large player comes in, it's in their best interest and in their incentive to do something that is not compatible.
Yeah, okay.
Even if you can read the schema, yeah.
Yeah, okay. Yeah. The other thing I really wanted to ask you is some part of the thing you said, it's really reminded me of the applicative state transition system of Backus. Any comments on that? Is it conscious or it just the same thing? You know, Bacchus's famous Turing Award lecture, talking about the applicative state transition system, which basically you got this purely applicative functional framework, but of course there is a state, and that state is just one and global. So it's not this sort of scattered state of imperative programming, but there is a state, which is, it's like your time ordered thing. It's really like a time ordered database. So any comments on that?
Yeah, so it's not all data is linked to each other in this system. It is still sharded per user. And there's some stuff I didn't get into in the presentation with collaborative use cases, and even doing after the fact ordering of multiple and merging of multiple event streams. Like we can do all of that, or at least large cases for it. But fundamentally, everybody has their own stream of data that's linked, and other people are going to be updating out of band. So for some things, yes, but just like, you know, again, in this idea, you know, FP idea where you have, here's my state, and in my scope, I understand all of it. But in the larger scope, there's probably other things going on that I'm not aware of. You're encapsulated to that one user unless you have a reference to some other piece of data. So it's not one large thing that has a single data root on it. It's a bunch of them.
Yeah, okay. Thank you very much.
Yeah. Yeah.
KK has one more question for you.
Mm-hmm.
Hey, yes. I was wondering, because you mentioned in the talk like various uses of cryptography, and I was wondering whether there are any innovations in the cryptography that you use, you know, or at least maybe less standard or lesser known cryptography. And the follow-up question is any of those parts implemented in Haskell?
So we're sticking very much with tackling the complexity that we know how to tackle and that we're expert at. Rolling your own cryptography is super dangerous. So we're using Kryptonite as our
cool, yeah,
as the source for all the actual crypto. Yeah, we currently support AES, so symmetric, fast, secure, symmetric system. It's also quantum resistant as well. So even when quantum computers become a thing, that's not breakable. And also baked into the browsers. RSA, 2048-bit keys, and elliptic curves, specifically the Edwards curve. So we did a look around at all the different elliptic curves. This is basically the most preferred from the community, though it's not available in browsers, which really sucks. The NIST, the National Institute for something, scientific technology maybe, has their own elliptic curves, but there's some skepticism about those specific ones. So we went with Edwards. It's very fast. Again, we've seen sort of in our rough benchmarks sort of 20 to 80 times faster than RSA at the same level of security, which is fantastic. The main innovations that we've done with that cryptography, we sort of from first principles reinvented crypt trees, which we then realized were not original. Other people have done them before, which was then great because we could take those and take their extra learnings and experience and apply them. That's probably the most unique thing about our system, is the way that the crypt trees interact with so this recursive encryption for the private side of the file system, how we can make that work with users having their own public-private key pair, and have that be totally user-controlled and user-owned. But that's not inventing something new in cryptography. That's just merging to existing ideas in an interesting way.
Yeah, sure, thanks. So just to clarify, these crypt trees are they're based on elliptic curves, is it?
So okay, yeah, I'll go into this a bit more. So each file or directory has its content encrypted with an AES 256-bit key. So that's a symmetric key. That's quantum resistant. Basically provides such high degree of randomness that even a quantum computer would take, huge amount of time to break it. It's not an elliptic curve. It's on a different principle, because it's elliptic curve cryptography is asymmetric, right? So you have a public and private key pair separate. So this is all symmetrically encrypted. And then as we go up each layer, we use a different key to encrypt its contents. Or at least the index for it. We then do key exchange. So you can do with public and private keys, they're much slower and bigger, but you're able to send messages to a particular recipient in an encrypted way. So we send them, or we store in this encrypted method, the key for the root of the thing that they're allowed to see, the symmetric key. Doing that first, unwrap and decryption takes time. That's the most expensive portion of this operation. It doesn't take like human scale time, but it takes computer scale time, right? More than the symmetric key. Now, once you have that symmetric key, decrypting everything underneath it is very quick. We have another performance optimization on top of that says, well, we know that at this level and below, you're allowed to see all of that. So instead of going to the network and grabbing each separate link, we're putting everything in a single JSON file, including the keys and pointers to the files, and encrypting just that one file. So we grab the one file off the network, and now you can have an in-memory data structure that's fully unencrypted to do that. So that's, that's how those two systems interact. Does that make sense?
Yep.
Okay,
thank
great.
you. Just one last question, if I may. So you mentioned the choice of curve. Did you also consider curve 25019? So maybe this is quite standard, but because you mentioned that you chose the Edwards curve instead.
Yeah, we looked at a bunch. Sorry, curve 25519. Did you say?
Yes.
Yes. So Edwards curve is you use. So curve 25519 has several sort of like sub-implementations, Edwards curve being one of them. I'm trying to remember the exact details. We did this all back in December, but basically you end up with two keys. One of them is a curve 25519 and the other is an Edwards, which is a specific subset of points on the curve or something. I can't remember exactly. It's a slightly different parameter, but they need to work together. So it is curve 25519, yeah, but a particular implementation of.
Thank you.
Yeah, no problem.
So I think we need to wrap up pretty soon. And if anyone has a final question, now's the time to ask. I have one more question. It's a very kind of general question because I'm interested in people and what motivates them. And I want to hear why you decided to start this company, to work on this project. What experiences did you have and problems did you confront that led you to this kind of amazing adventure?
It's been kind of partly, I've been heading in this direction for a long time, I think, though maybe not this exact form, where I have always found that writing web apps, I was writing the same things over and over and over again. So I've always been looking for like, well, is there some way that we can abstract that out? And a lot of people, I've had various ideas over the years and like, oh, that sounds a lot like, parse in particular. If people remember parse would come up, or standardlib.io. Sounds like something like that. I'm like, yeah, something in that general direction. Then ended up working in standards on Ethereum for about a year, I guess, and realized, oh, okay, so I could, take my FP and distributed systems background And there's this other, once we apply cryptography to that, we get this actually surprising amount of synergy between the two fields, where we can start doing this stuff really, really at scale for individual people. What's the technology available right now? And how can we apply this in a way that, because there's definitely people that are doing blockchain or IPFS stuff as a blockchain or IPFS project. And looking at that space being like, yeah, there's lots of cool technology, but how can we apply this to actually solve this set of problems that have been bugging me for years, right? And is there a better way and a better way of architecting things? I also have a bit of a iconoclast, I guess, tendency to say, well, that's great, that's how it's done now, how could it be better? And again, just looking at, well, here's the tools at my disposal, here's the problems with the current thing, or the problems I'm trying to solve. What if we inverted some of these models, and just purely from a thought experiment side, and then realizing like, oh, we could actually probably do that. And finding it interesting and a good fit for my particular skill set. So kind of the short answer, I guess, is I made a job that fit me.
Yeah, you did actually. You invented your own job and a company to go along with it and hired yourself.
Yes.
Well, it's pretty remarkable and genuinely inspiring.
Oh, thank you.
What you're doing. Yeah, no, thank you. Thank you for the talk and for your time tonight. Thank you everyone for joining and asking questions. And I think we've gotten a lot of good speakers, and we are recording these sessions and putting them on YouTube. And to me, every single one we've done so far, and this one is no exception, is something that I will myself be watching like probably a few times. It's just really great to have this opportunity. Did I lose you, Brooklyn?
No, just still here. I just thought I would save some bandwidth while wrapping up. Yeah,
that's what I was doing. So it's hard to applaud over Zoom because there's always interference. So people can give you like a clapping emoji like that, or they can they can put their video on and wave their hands at you. So thank you very much for joining us. And I'm going to turn the recording off, and then if people want to just have a casual chat for a few minutes, if you can hang around, we can do that. And also, if anybody has an announcement that you'd like to make to the group, you can go ahead and do that. So I'm going to stop the recording, and thank you again, Brooke, for joining us. This was really tremendous.
Thank you so much for having me.